My name is Paweł. I'm a developer, like many of you today. I'm going to talk today about blockchain. It is a revolution in the making. It is something that's happening in the background that some of you might already know and some actually don't. So let's start from what's happening currently, now at the moment. I would say we just entered an information age. It lasts for a while, but that's what's happening now. So information age, by definition, is basically a period when there was a shift in paradigm from industrial-based production to production based on computers, networking, messaging, selfies, and all the bits and bytes flying around. So from a developer's point of view, I've handpicked few examples of what actually defines information age nowadays. So let's start from a simple one. This is open source. Yeah? So open source enabled us to collaborate, to share, to build products outside of any kind of governance. Actually, the best example of open source is node modules, the largest man-made structure on Earth. It's basically larger than the Great Wall of China by volume. So we have cloud computing, basically moving any kind of resourcing and cost to the cloud, leveraging the infrastructures in it. So and there is IoT, smart fridges, which can actually notify you if you are short on food or assess if you need something more, right? So the next thing that actually happened at the moment is machine learning. The example here is actually deep learning. This is all you need to get started and to experiment in that. Yeah? So pattern recognition systems, neural networks, recurrent neural networks, all of that. And the last example is agile, but let's not get ahead of ourselves and don't think about that just for now, yeah? So before we start talking about blockchain, I would like to introduce you to a few cryptographic concepts that blockchain is using, that blockchain is actually based on, right? So cryptography is a way of securing communication. I think everyone knows that, yeah? So starting by the hash function, a hash function is a function that loses all information. I mean, we all wrote functions like that in the past, right? Some of us still do. So basically, we have our input. The definition of a hash function is basically an input that we have an infinite input that actually can be reduced to a fixed length output. So this is called a key, a message, an input message, just an example. So by running it through the hash functions, we are receiving a hexadecimal value, which is called the message digest, right? So it's actually it doesn't contain the input value. It actually allows us to verify its integrity. So hash function is built from two things. It contains a good one, at least. It contains a hash code map, which basically, on the first step, maps the infinite set of keys to some unbound integer values, right? And then there's a completion map, who basically maps that integers to a reduced set of values. So why do we actually care about that? So this is the form of a hash function. It's basically a composition of two functions, hashcode map and completion map. So what blockchain uses is basically a cryptographic hash functions who has several distinctions. I mean, every cryptographic function is a hash function, but it has some distinct features. So a good hash function should be quick to compute, should be deterministic, so it should result in the same value in every run. So it should be one way only. So it should be like, from a computation point of view, it should be really infeasible to run the computation and try to decode the input message. So it's like 1 and 77 zeros of options to run through. So a good hash function should be actually collision resistant as well. By collision, I mean that there are two types of collisions. Hash code collisions, when two hash codes provide the same result. And the second kind of collisions where two hash codes compressed actually to the same value. So moving a bit forward. So there's a bit of difference between what's happening in the blockchain in terms of cryptography. So hashing is not encryption. Hashing is a way, basically, it's not a way to store information, it's a way to verify it. Yeah. So encryption, on the other hand, is used a bit differently in blockchain. So consider we have an input. We run this input from a generated key using OpenSSL or something else, a key generated by us. We cipher the input, basically. So after running into a key, it's encrypted, it's encoded. So we can decrypt our message using the same key we generated, right? So this is the basic of encryption. And blockchain uses something that's called a public key cryptography. So we actually have two sets of keys. We generate our private key and derive public key from the private key. So they are mathematically related. So we can just expose the public key to other parties that want to send us some kind of encrypted message that only we can read. Yeah, so that's the premise about it. So we have another concept in place when it comes to blockchain. It's called digital signatures. Yeah? So it's a way of sign of transactions or sign of movements or sign of our actions that are happening on blockchain. So in a way that someone on the receiving end can actually know that this is coming from us. Yeah. So in terms of blockchain, there are really two concepts when it comes to cryptography. The first one is who sends the transaction, and the second one is that the past cannot be really altered. So digital signature, it's basically our hash encrypted with our private key, broadcasted to the wild, and basically everyone that receives it and has our public key, remember they are coming in pairs, can actually verify that it's coming from us. So another concept, very crucial in blockchains, is called Merkle Tree. So just remember, because I'm confusing the name a lot, it's not Merkle's tree, it's actually Merkle Tree. So if you consider a hash function a way to provide a unique one-way identifier to an input value, to a message, you can consider Merkle Tree as basically the same for collection of messages or collection of values or collection of data. So it actually also loses the information. It produces a footprint that can be easily verified. So let's see how we can construct actually the Merkle Tree. So consider we have 4 chunks of data, right? So we calculate we are applying hash functions to every single chunk of data. We calculate the hash for every single chunk of data, and this creates what's called a leaf node in Merkle Tree. So by definition, Merkle Tree it is a binary data structure that consists from a node that has always 2 successor nodes. So based on that, then we just calculate the results of the hashes of the leaf nodes and apply the hash function again, creating the parent nodes. So, and then we concatenate the values from the parent nodes and apply the hash function again, and we create something what's called a root hash. So it's like the base, the main identifier of all values that are stored in the Merkle Tree. So consider the example on the right. So there's some slight difference, right? So the input changed. So we have another data value that the Merkle Tree is constructed from. Yeah. So just a single and slight change can result in completely different root hash. So it actually improves a lot in terms of checking for equality. So consider a scenario that happens a lot in peer-to-peer networks when someone sends us a root hash, a chunk of data, and tells us that basically this data is included in the set that's Merkleized. Yeah, so it is an untrusted peer. So one way we can verify if it's saying true or not, or false, is basically we can ask for the remaining 3 points of data, and we can run our hash functions through them. So this is not effective because it actually increases the network footprint. It increases the number of computation that needs to be done on a node in a network. Yeah, so there's a better way to do that. So upon receiving the value from a trusted peer, we can just compare this value to what we have already, right? And if the hash and just go from there, right? It's called a hash path. So basically, we are trying to calculate the root hash here from the values that are sent by the untrusted peer. So upon calculation, we can clearly see that if the root hashes of the messages digesters are the same. So as I said, it really reduces the network footprint. It reduces the number of computations that we need to do. So we don't need to compare all sets. We just need to rebuild the tree using a proper path. So another concept of blockchain that blockchain is basically made of is decentralization and distribution. So, I assume this is a well-known page from a book called On Distributed Communications by Paul Baran. So let's see what it actually means being centralized, decentralized, or distributed in terms of technology, system, or just agnostic way. So a centralized system is a system of governance, basically. Think it about like a client-server system. It has its own set of rules. It enforces this set of rules on the client. It's monolithic in nature. It's easy to build, hard to maintain. It's basically a single point of failure. So at decentralized systems is where actually the curiosity happens. Yeah. So the decentralized system can be defined as a system that is not under any kind of ordering influence, right? So it is a system where all nodes in the network are equally privileged and are working towards common goal, with no saying which one node is better or has better rights or has better priority to compute things. So a distributed system basically is a system where communication and coordination happens through messaging. So distributed systems are actually pretty easy to scale. I think they basically scale in infinite way. So blockchain is basically built upon these two concepts. It's actually distributed and decentralized at the same time. It's mirrored across 1,000 of nodes with equal rights to compute. It's not easy to take down unless you take over the nodes, to which I will refer a bit later on. So it's not a simple task to provide a concise definition of what a blockchain really is. Every one of you has its own definition what it is and how it's evolved. But by finding 5 words to define blockchain and to actually express what it means, we can start by saying that blockchain is distributed. So the nodes in a blockchain network are basically coordinating their actions through messaging, communicating, updating all the time, speaking to each other. So blockchain is actually decentralized. So there is no governance in blockchain. So no one tells a blockchain network what the network needs to do. and what to work on. It's a collaborative effort. It's the power of the small. So blockchain is actually secure. It's powered by state-of-art cryptography, and it actually goes two ways, because there are some attacks that can compromise a blockchain network. I think that most of the times they're not really feasible from a computational point of view. So the last three words basically that blockchain is. One can say that blockchain is basically an immutable data store. So by immutability, it's not that kind of immutability that we actually are meeting on every day writing our code. It's a rule, basically. It's very hard to alter the state of a blockchain network. So consider the block. It's basically the building foundation of a blockchain from a technology and protocol agnostic point of view. This magnificent structure can be considered as basically a genesis block, which means that this is the first block that arrives on the network. If I'm not mistaken, a Bitcoin client is actually embedded in the very first genesis block, which was mined and created and pushed to the network. It actually has some interesting information encoded within about the state of financial and government affairs back then when the protocol was published. So block is basically a data container that for transactions. That's the simplest definitions I can came up with. So it consists of a block size, a block header, transaction counter, and the actual transactions. So block header actually has its own characteristics. It's made of a version. It contains a previous block hash, which is actually a link. It contains a Merkle root hash, which has all the transactions Merkleized. It has a timestamp, just to point to his date of creation. It has a difficulty value and a nonce value. So basically, difficulty means how difficult it was for the peers to create a block and put it on a blockchain and link it together with the previous blocks. And nonce is an incremental algorithmic value that tells us how actually it's related to difficulty. It's incrementing with each step of mining. So let's consider the transaction. So from a distant point of view, someone looking at the blockchain can think that a transaction is basically a physical value, right? That the coin is basically a physical value, that there are some files stored in the blockchain that are being moved around on request through the peers in the network. So this is not really true. So a transaction is basically a transfer of ownership to another account, right? So transaction in blockchain looks exactly like this. It's a public ledger, right? So like an accounting ledger. So it actually lists the transactions that the other peers made on it, right? So this is all it consists of. It can be multiple transactions that are encoded in a block. So the definition of a transaction is every transaction includes an account, a sender, an amount, and a receiver. Just don't be fooled by the coins. This is the Bitcoin protocol, just from a distance. Other implementations are moving data through transacting them to the network. So what's really the chain, how the linking looks like? So this is basically a block with all the information we talk about embedded in it. It has a header hash, it has a previous block header hash, which is basically the link, timestamp, difficulty, nonce, and the Merkleized transactions in it. So basically, this can be seen as something that happens from the middle of the chain, right? So then the next block that arrives upon a collective agreement to which I will refer in a moment, actually links to the previous hash or to the hash of the previous block. So, but really, how it happens? So, every transaction is bundled in a block, and how they actually arrive to this block. Imagine a situation when someone wants to send some money through blockchain flowing from one person to another, right? So it needs to have some kind of cost involved of that kind of operation. It's not free. It doesn't happen immediately. It doesn't arrive in a quarter of a second, perhaps in 3. So in order to incentivize peers in the network to help just run these kind of transactions and move them through places, there's something established in the Bitcoin paper which is called the proof of work. So proof of work is basically a kind of consensus. It's well, all nodes agree on the same world state. So whenever a transaction happens, whenever an asset is moved from one place to another, all peers in the network can actually decide if that's happening or not. It's all public. So that leads basically to the creation of a new block, but how it really happens. So every node in the network basically takes awaiting transactions from the pool, which are broadcasted through the network. It adds a nonce to them, which is a random number of incremental value. It hashes it all, and in the end, it checks the leading zeros of the hash. So if our node's check of the zeros just fulfills the agreement of other nodes, if it's basically equal to the zeros that are computed and agreed on in other nodes, the miner who actually does the computation receives a reward, which is a coin, like a Bitcoin or a fracture of it, or some kind of reward in order to incentivize him to do so. And the difficulty rises. So upon creation of a next block, it's just more difficult to generate a next block because the algorithmic complexity rises. It's basically a computational puzzle to be solved from each participant. So if that's not the case, we are just going back to square almost zero. We are just running the algorithm again and hoping that this time we can win the reward. And this leads actually to creation of a new block where all of the transactions are stored. So one thing to remember when talking about blockchain networks, that you are basically just a node. You are just a peer that cooperates and collaborates with others. So there's no such thing like being connected to a blockchain network. So imagine a situation when you want to alter the chain of transaction that was mined and agreed on, and the heaviest chain, for example. So you corrupt this chain on your local instance because the data in the network is made publicly available to every participant. So it's a copy that's replicated endlessly to nodes, right? So whenever you try to corrupt, you are just creating a fork. You are branching out from the main chain, and no one actually pays any attention to you anymore. No one wants to collaborate on the set of data you just corrupted. So this actually defines security. I mean, the power lies in the collaboration of others, in the validation of others, in the proofs and verification of a hive mind. So let's talk a little bit about the history of blockchain. So in 1991, Stuart Haber and Scott Scornetta actually published a paper about cryptographically secured blocks, chain of blocks of data. So Dave Bayer joined them and added his own input, which is basically a collaboration depicting Merkle trees added for efficiency and storing multiple data in a block. So then Satoshi Nakamoto appeared, and actually no one really knows who he is. Might he be a collective hive mind or just a person who chooses to remain in the shadow? He published a paper about Bitcoin, the first distributed ledger of all transactions, the first way of moving assets through a network without a third party, without the governing body. So he actually established a way of delegate trust to the many, of delegate trust to the network without any governing control. And then blockchain 2.0 happens, which actually introduces smart contracts in its logic. The term smart contracts was coined by Nick Szabo before actually the actual Bitcoin paper was produced, right? So Nick Szabo worked on a concept called BitGold, introduces smart contracts, to which I will refer in a second. And the protocol implementations evolve in a way which incorporates them. So I would like to talk a bit about Ethereum. So Ethereum is another blockchain protocol. It is an implementation of the same premise, but made with some substantial and significant differences. So Ethereum was created by Vitalik Buterin, which is a young programmer residing in that time in Canada. And he actually wanted to change the things works. He wanted to evolve the blockchain itself. So two concepts were introduced in Ethereum that are lacking in the Bitcoin implementation of the blockchain. So first concept is basically smart contracts. A smart contract is a decentralized node that basically, after meeting a certain condition, is guaranteed to execute the logic in it. So think about it as a decentralized code launching on every node upon certain conditions. Think about it like a transaction which is extended to include infinite moving pieces. So smart contracts execute symmetrically across all nodes. They are with no physical location. They just live on the blockchain. So other concept that Ethereum is based on is the concept of decentralized applications. So it is a centralized front-end code with decentralized backend. This is an interface to Ethereum, for example. So if a decentralized application is an alphabet, a smart contract is a letter in this alphabet. And there's a lot of movement because of the dApps that are being created at the moment. So an example of a smart contract is just a piece of code from a voting application that can be deployed on a blockchain like Ethereum. So it's written in Solidity. Solidity is a Turing-complete language forked from JavaScript with some additions from C. It's very robust, and it allows us to implement almost infinite logic on the blockchain. So the decentralized applications actually provides a way to interact with the blockchain. So in case of Ethereum and the voting app, it is just a simple front-end interface interacting through a Web3 JavaScript library through remote procedure calls with the Ethereum virtual machine. It's basically used for deployment and handling of the logic. So a smart contract can actually work with the outside data, but there are some ways to prevent it. So with Ethereum, the term Web 3.0 was coined. So blockchain enthusiasts are just often convinced that this is the way technology is going. So we are moving from a centralized resources like AWS or Azure to a decentralized stack, which is maturing from day to day. So this is an abstracted stack made by Stefan Tural. It basically provides a point of view of what's happening in the technology and how it is evolving. So on the top we have decentralized applications browsers, like the clients to the Ethereum, for example, that allows us to move the data around or to do the transactions, to push transactions to the blockchain. So other decentralized applications which are worth mentioning are Slog, IT Gnosis, and actually Golem, which is not on the graph, but I will refer to that a bit later. So other layers are actually just as interesting as well. So for storage, there is IPFS. It is a decentralized storage that promises to store your data on a network of peers, of nodes. From what I know at the moment, IPFS is actually in constant development. They're working on a layer that will incentivize peers to actually store the data. So remember, they need to have some kind of interest of doing so. There's nothing for free. So Ethereum also introduced a concept called digital assets. So by digital asset, I understand, for example, a transaction, because this transaction is a registry, what happened on the blockchain, so it can serve as an asset. So let's start from coins. Basically, how we understand coins now, they are just a piece of commodity used for trade generated by government. And they actually can be just as well generated by blockchain using the proof of work. So they came for doing the work, they came from computational complexity of generating them. And by that rule, they actually achieve value. So Bitcoin generates Bitcoin. So Ethereum has Ether, which is basically, at the moment, it's the second highest priced coin, just excluding Bitcash for a second. So there's actually, there are also tokens. So these are interesting things where all the blockchain dynamics is happening around. So a token is basically an asset generated by a decentralized application. So for example, moving to a Golem example, which is an application that provides distributed workloads. So no matter how large your workload is, you can basically distribute it across the network and speed up whatever you want you are doing. So in order to do that, you need to buy tokens on the platform, either for Ether or just for using some another resource. So another concept of a digital asset is basically a security. So a security is some kind of tangible instrument that basically can be leveraged and traded for another of the same value. So and what's happening in the background at the moment is a new way of doing startups. So decentralized apps is just a new keyword for a startup. Initial coin offerings is a way to crowdfund the startups. So you just, for example, you buy a cryptocurrency, use Bitcoin or Ether, and you just move this cryptocurrency to a startup that's doing the ICO. And this is a double-edged sword because the production cost, the development itself costs real money, right? So hiring developers, hiring top minds, and producing the decentralized app that was promised costs real money, and the market of cryptocurrency basically fluctuates. So now, just let's talk about, just for a bit, what are actually the disadvantages of blockchains and blockchain 2.0 platforms like Ethereum. Because all of this might sound just a bit utopic. So, firstly, client security. So blockchains are built secure by default. They are secured by state-of-art cryptography, right? So, but the clients that actually interact with blockchain networks aren't. So there was a case of Parity, which is a decentralized app browser handling the Ether transactions on Ethereum. And actually, the hacker all the hacker needed to do is just to replace the address in the client, which is written in JavaScript plus some JS framework. And this is actually a big thing, because even if blockchain is secure, whatever works on top of it might not really be. So another thing is bug-free code. So no one really writes bug-free code besides the person you see in the mirror. So, and the contracts are a special case of it, because once a contract is coded and deployed, it's immutable. It cannot be changed. It cannot be overwritten. A new one can be deployed, but it actually comes with other difficulties. So that's another thing, which is scalability. So Ethereum at the moment can handle like 11 transactions per second. So there are private blockchains handling much more using different consensus algorithms. But the future doesn't really look good. So because of the rise of the ICOs, a lot of platforms are being built on top of the Ethereum. And it does tax the networks really, really bad. So Ethereum Foundation is actually working on a solution to this. The Metropolis hard fork, I think it arrived this week, or will arrive on Monday. By hard fork, I mean a complete rewrite of set of rules on the blockchain network, to which the other nodes will need to accustom. Hopefully, it will solve some scalability issues. Other solutions are on the way. And there's actually a problem of governance. So while doing typical money transactions using PayPal or a Swift banking transaction, you have a governing body that controls the transaction and makes you sure that everything will go okay with it. So in a public blockchain, in a public ledger, by definition, there's no concept of a firm. There's no concept of governance. So there's no governing body. There's just decentralized nodes collaborating with each other. The trust is delegated. But there is some kind of governance, right? We have a set of developers who's actually writing the code, who's deploying the networks, who's doing hard forks, who is setting the rules. So it might be something to think about. And there's also a human factor. So doing blockchains requires collaborations on many levels, from professionals ranging from laws, crypto security, experts, programmers, domain experts. So it all needs to fit together. They all need to collaborate. And as we know, this might not be always the case. There's often a conflict of interest and a different set of goals for each party. So let's talk about blockchain adoption, what's happening on the market at the moment. Actually, Poland has really good successes in terms of adopting blockchain. So it started doing blockchain before it was created. Yeah, this is a building in Gdańsk. It's called the Waveler. So you can see how the blocks, this is a heavy chain. So a lot of Ethereum-based startups arrived, and most of them are closing to completion. Some of them are done. All of them are really interesting. For example, Golem is a Polish-based blockchain Ethereum startup who promised to provide a way to distribute the workload across the nodes. So no matter how complex your problem is, you can just distribute it to a nodes that have some incentive and compute it really fast. Unrise is speech recognition using blockchain. Allies.se is basically a way to expose the trust for charity. So whenever a charity is founded, it's stored on the blockchain. It's public, it's transparent. Everyone can see what's really happening in there. So there are two cases I want to talk a bit longer. So first platform that I want to mention is Stock.it. It's basically an IoT plus blockchain solution. So Stock.it promises, in an oversimplified way, replacing the way the security works now. They actually are using Ethereum and their own Ethereum nodes to provide a decentralized security with no requirements towards a physical key. All on blockchain, all digital. Other initiative that Stock.it realized already is the share and charge initiative. So this is a Raspberry Pi Ethereum node connected to a charging station. It is connected to an Ethereum network, and there are over thousands of this kind of nodes in Germany. And it actually allows for complete non-government form of payment for energy. So the other project I would like to talk about is the Untitled. Untitled is being made by Connaxys. Connaxys is a market-leading consulting firm who's actually heavily investing in blockchain technologies. So, for example, they have already made steps and have heavy blockchain presence in a project which is called MakerDAO. So, what's interesting about Connaxys is that basically they're pioneers program. So, they are investing in building teams, training them from scratch, and moving them to projects that matter. So the Untitled is it's a little about games, but not necessarily. I am a gamer at heart, so this basically interested me. So it is a way to provide gaming to a lower income groups. So think about Steam as a centralized governing system when you have to pay a huge 30% like royalties to Steam. So what Untitled aims is a system based off Ethereum that's basically royalty-free, but for producers and consumers, like the gamers itself. So it is a licensing system. So instead of publishing a game of Steam and just spending the royalties, you can publish the license for it on Ethereum. So why should you care about the technology? What's really happening around that? It can be used to multiple purposes. It can be just the amount of projects and the capacity of the technology is basically infinite. But let's talk for just a bit about identity and why it matters. So for now, how identity works, for example, your own government-based ID where you have your name on it. So it works in a centralized way. Government is responsible for handling all your data. So think Equifax and how it ended last week or 2 weeks before. So using blockchain technology, we can change that approach, right? So we can store our identity on the blockchain and be sure that it's not going to be altered or lost. So with identity, it also comes reputation, right? So reputation can be also made immutable and stored on blockchain. So think about eBay comments or Amazon comments or even manufacturing process when you have your most beloved sneakers and the hash of the sneakers is basically cryptographically imprinted on the blockchain during manufacture. So you can always tell whether they are valid or not. So there's also a bit of danger related to this technology. So basically, few weeks ago, China decided to deregulate cryptocurrencies. Yeah, they decided to deregulate ICOs, crowdfunding ways to found a startup. So And it shaked the market a bit. So there are some suggestions that all of this is just about the control of flow of the capital. And I'm not really 100% convinced that this will just go away, right? So we can talk a lot about cryptocurrencies, about regulations, about freedom, about transparency. But in the end, some kind of regulation is what is going to happen sooner or later. So this is an obligatory quote that tries to be smart. Do you notice the patterns that are happening at the moment? So for example, Facebook is a platform for content generation, but it doesn't generate any kind of content, right? So Alibaba is the biggest marketplace with no actual inventory in it. Uber is a way of move people around, but it doesn't possess any kind of fleet of cars, right? So blockchain might join the circle. So it basically, immutability and trust delegation will probably come a long way. Thank you.